When students hear ocean chemistry, they often imagine a list of ions or a table of numbers. That's not our goal here. Ocean chemistry is about explanation. What substances exist in seawater? Why seawater has a surprisingly consistent composition? And why some substances vary dramatically over space and time. Today, we'll keep returning to one big idea from the previous lecture. Water's molecular structure makes seawater possible. Water is polar. It forms hydration shells around ions, and it dissociates slightly, giving us the chemical foundation for acid-base reactions. Without these properties, the ocean would not be the vast reactive reservoir of dissolved material. It would be chemically inert by comparison. Seawater is a solution, meaning it consists of a solvent and one or more solutes. In seawater, the solvent is water. The solutes include dissolved ions like sodium and chloride, dissolved gases like oxygen and carbon dioxide, and many other dissolved compounds. Importantly, these substances do not exist as dry salt floating around in the water. Once dissolved, salts separate into ions. Why does that happen so effectively? Well, because of polarity. Water's polarity means it has regions of partial positive and partial negative charge. When an ionic compound enters water, water molecules surround each ion. The oxygen end points toward positive ions, and the hydrogen ends point toward negative ions. Opposite charges attract. These electrostatic attractions stabilize ions in solution and prevents them from recombining into crystals. Salinity is a quantitative measure of how much dissolved material is present in seawater. Specifically, it refers to the total concentration of dissolved inorganic salts. On average, seawater has a salinity of about 35 parts per thousand, meaning that 35 grams of dissolved salts are present in every kilogram of seawater. Salinity is not uniform across the ocean, but the composition of seawater is remarkably consistent. Understanding why that consistency exists is one of the central questions of ocean chemistry. Although many substances are dissolved in seawater, a small number of ions dominate. Chloride and sodium alone account for over 85% of dissolved salts by mass. Other important ions include sulfate, magnesium, calcium, and potassium. These ions enter the ocean through processes such as rock weathering and volcanic input. But once present, they persist for long periods of time. The dominance of these ions are not accidental. It reflects both the effectiveness of water as a solvent and the long-term balance between inputs and removal processes in the ocean. Let's take a closer look at some of these ions. A conservative substance is one whose concentration changes only with dilution or concentration of seawater, not because it is actively added or removed. Sodium, chloride, and the other ions that we just spoke about are classic conservative ions. Their ratios remain nearly constant throughout the ocean. We will come back to this in a moment. But first, let's talk about non-conservative substances. Non-conservative substances, by contrast, are influenced by biological activity, chemical reactions, or physical removal. Nutrients and gases such as oxygen and carbon dioxide fall into this category. Let's go back to those conservative substances we were just talking about. All of the major ions in seawater are conservative. This observation is known as Forchheimer's principles of constant proportions. This principle states that the major ions in seawater maintain nearly constant relative proportions worldwide. In other words, seawater can be concentrated or diluted, but the main ionic recipe stays the same. This is why salinity can function as a chemical sort of master variable. If you know salinity, you can predict the major ion concentrations with good accuracy. Not because the ocean is static, but because the processes controlling major ions operate over long time scales, and the ocean is well mixed relative to those timescales. This principle is also why oceanographers historically use chlorinity as a proxy. Chloride behaves conservatively, so its ratio can indicate the total salts of the ocean. Residence time refers to how long, on average, a substance stays in the ocean before being removed. Major ions like sodium and chloride have residence times of millions of years, which explains why their concentrations are so stable. Shorter residence times indicate active cycling, are most likely non-conservative substances such as oxygen or carbon dioxide that may be utilized by living organisms. In addition to dissolved salts, seawater contains dissolved gases. The most abundant of these are nitrogen, oxygen, and carbon dioxide. These gases originate primarily from the atmosphere and enter the ocean at the air-to-sea interface. Once in seawater, they behave very differently from the major ions we discussed earlier. Unlike sodium or chloride, gases are not permanently stabilized in solution. Their presence in seawater depends on physical conditions such as temperature and pressure, as well as on chemical reactions and, later, biological processes. For that reason, dissolved gases are almost always non-conservative. Their concentrations vary widely with depth, location, and time. Temperature is especially important. Cold water can hold more dissolved gas than warm water. As water warms, gas solubility decreases, and gases are more likely to escape back into the atmosphere. This temperature dependence alone creates large spatial patterns in dissolved gases across the ocean. It's important to recognize that dissolved gases are not just passive tracers. Once gases dissolve, they become part of the ocean's internal chemical system. Oxygen can participate in oxidation reactions. Carbon dioxide, as we'll see next, does something even more interesting. It reacts with water itself. That distinction makes carbon dioxide chemically unique among the dissolved gases. At this stage, we are not yet concerned with how gases move across the air to sea boundary or how circulation distributes them. Those processes belong later in the unit. Here, the takeaway is that seawater is chemically open to the atmosphere, and dissolved gases introduce variability and reactivity into the ocean system that salts alone do not do. Carbon dioxide deserves special attention because, unlike nitrogen or oxygen, it does not simply dissolve and remain unchanged. When carbon dioxide enters seawater, it reacts directly with water molecules. This reaction forms carbonic acid, which is unstable and quickly dissociates into other chemical species. As carbonic acid dissociates, it produces bicarbonate ions and hydrogen ions. Some bicarbonate can further dissociate into carbonate ions, releasing additional hydrogen ions. These reactions are reversible, and the relative abundance of each form depends on the chemical conditions of the seawater. Pause the video for a few minutes if you need to take a look at this figure to understand those reactions, and focus primarily on the production of these hydrogen ions across these reactions. This set of linked reactions is known as the carbonate system, and it is one of the most important chemical systems in the ocean. It exists because water readily participates in acid-base reactions, a property that comes directly from water's ability to dissociate into hydrogen and hydroxide ions, which you learned about in the previous lecture. The production of hydrogen ions during these reactions means that carbon dioxide directly influences pH. pH is simply a measure of hydrogen ion concentrations, so any process that adds or removes hydrogen ions will affect pH. In seawater, most dissolved carbon dioxide does not remain as CO2. It exists primarily as bicarbonate, with smaller amounts of carbonate and dissolved CO2. At this point, the key idea is not to memorize the reaction equations, but to understand that carbon dioxide fundamentally alters seawater chemistry by creating a dynamic balance among multiple chemical forms. This balance allows seawater to absorb carbon dioxide while resisting large, rapid changes in pH. For now, what matters is recognizing that carbon dioxide connects the atmosphere to ocean chemistry in a way no other major dissolved gas does. It is the bridge between physical gas exchange and chemical regulation within seawater. We will discuss this more in later lectures. Seawater is slightly basic, with an average pH of 8.1. This value reflects the balance between dissolved carbon dioxide and the buffering capacity of seawater. Seawater resists rapid changes in pH because of buffering. The carbonate system can absorb or release hydrogen ions depending on conditions, preventing extreme shifts in acidity. This buffering capacity exists because water is both a solvent and a reactive chemical participant. And without this buffering capacity, the chemistry of the ocean would fluctuate wildly, making it far less stable over time and less likely to support life. It all comes down to the uniqueness of that water molecule. So if you take only one idea from today, it's this. Ocean chemistry is not an add-on. It is a consequence of water's molecular behavior. Polarity allows salts to dissolve and remain in solution. That creates salinity and supports Forshammer's constant proportions theory. Water's dissociation and acid-base behavior make pH meaningful. Carbon dioxide reactions create the carbonate system that buffers and stabilizes the oceans. Every single chemical behavior we have discussed today is rooted in the molecular structure of water. No other molecule could do this. Next, we move to air-sea interaction. You probably know water stores heat and requires large energy for phase changes. That was the water properties lecture. You now know seawater holds gases and CO2 reacts to influence pH. That was today. Air-sea interaction is where those ideas meet at the boundary between ocean and atmosphere. The sun's radiation and atmospheric heating will become important factors that generate the air movement we generally call wind. And we will eventually learn this wind is what drives movement at the surface. And that water movement is critical for circulating nutrients and dissolved gases to all parts of the ocean. And of course, those dissolved gases and organic nutrients are what makes life possible throughout the oceans.